Ladies and gentlemen, dear colleague, good morning. So it's a great pleasure for me to be here with you today, and thank you to Professor Inoue for arranging this this seminar. So what I would like to do is to tell you a little bit what we have done in a frame of a project. But before starting, I just briefly would like to introduce the place where I'm coming from, if this works. Aha.
Yeah, you don't want.
I can do it by.
No.
That's true.
You can click here maybe. Yeah. This is now the
Yeah.
Now you can use.
Okay. So I'm coming from a city that is called Toulouse, and Toulouse is located in the south of France. So I put Paris here. So straight to the south, you find Toulouse. And I'm working in a CNRS lab that is the coordination chemistry lab. That is a lab that has been created just 50 years ago. And in this lab, the research group are developing different topics, all somehow related to inorganic molecular system. So the different topics the people are working in are catalysis and organometallic chemistry, molecular material and nanomaterial, and bioinorganic chemistry and the role of metal in biology. So there are roughly 200 people working in this lab. So Toulouse is an old city, yeah, 2,000 years old at least. And so here I choose a few pictures just to give you an idea of how this city looks. Today, Toulouse is also famous because of the plane industry. So in Toulouse, we have a huge factory of the Airbus planes, and Airbus is located actually in Toulouse. But let me move on and start my scientific topic. So we have been interested many years ago in the topic of molecular nanomagnets, and especially the single chain magnets. So when you want to make such kind of system, you have to control several aspects. These aspects are the chemical topology. So if you want to have a single chain magnet, chemically you must be able to construct like that, something like that. But another very important aspect is the magnetic anisotropy, because you need magnetic anisotropy to have the expected magnetic behaviors. And for that, you have to implement these into the building block. So the building block we needed are complexes having a large Ising type magnetic anisotropy. And when you have that, and when you are sure that this anisotropy is not going to change when you do chemistry, then you can use these pieces to construct, let's say, the targeted systems, magnetic systems. So in this, before starting, I just like make sure maybe you are not all familiar with the concept of single molecule magnet or single chain magnet. So the view of let's say the simple view you can have on these kind of compounds is to say, okay, a complex like that or a chain structure actually can behave like a magnet. So the behavior will be similar to that of for a traditional magnet. And so this means that when you have, let's say, a sample with a large number of molecules, of course, these molecules will be, the magnetic moment of the molecules will be oriented in any direction of space. And then you can apply a magnetic field to magnetize the compounds. So what happens is you are going to align the magnetic moment of each of the molecule with the applied magnetic field, and this results in a magnetization of your system. And this will remain stable when you switch off the field, because there is an energy barrier that avoids the relaxation, because to relax, the spin has to cross an energy barrier. So it stays magnetized as long as let's say the temperature is below a blocking temperature. Of course, if you increase the temperature, what happens? You will see a relaxation of your system and you lose the magnetization. But what you have to keep in mind is that the magnetization you measure is not coming from a magnetic order. It is just the molecules, individual molecules that are magnetized. So what is important here is the energy barrier that will stabilize your magnetized system. And this energy barrier here is something you can somehow design. And to have a large energy barrier here, there are some important, what I call ingredients, that is to have a large ion anisotropy, because this will stabilize or help to magnetize your compound. You need also a large spin constate, and if it is a polynuclear system, you need also efficient exchange interaction between your spin centers. So what we needed is a building block that would be adapted to make, let's say, the chemical topology, but also that would be providing sufficient magnetic anisotropy, and the magnetic anisotropy that is actually controlled. And this is the reason why we started working on a specific geometry that is the pentagonal bipyramid metal complexes. So in a coming minutes, I would like just to briefly explain why and how we can play with the magnetic anisotropy of such kind of species. So here are drawings, and these are views of crystal structure of such complexes. So these are complexes that have 7 coordinated surrounding. And these compounds actually are known since a very long time. So in the 70s already, the people discovered how you can make such kind of compounds. Actually, to access to such kind of geometry, it's quite easy. What you need is an adapted ligand. So the ligand you need is a pentadentate ligand, like this one here, that will actually occupy the equatorial position of your metal center. So you have 5 atoms that will coordinate to the central metal in the equatorial position, and then you have 2 additional coordination sites in the apical position. So this is possible with the open ligands like the one that is shown here, or with microcyclic ligand like the one that are here. So chemistry for that was quite well established. Of course, at that time, nobody was looking the magnetic properties of such kind of compounds. So why is this geometry interesting for the magnetic anisotropy? So here what I show is the energy diagram of the d orbitals in the ideal geometry. Of course, in this ideal geometry, you have actually degenerate levels like here and here, but this exists only in the ideal geometry. In the real compounds, there is a slight distortion that lifts the degeneracy here, and you end up with an energy diagram that roughly looks like this here. And now you can put some electrons. For instance, here I show 2 examples. So D6, this is for iron 2, D7, this is for cobalt. And so you see, we have species that have a spin 2 and a spin 3/2 for these 2 ions. So In such a situation, actually, what happens is you have the zero field splitting that will act on these compounds, and the magnetic anisotropy actually results from the zero field splitting. So I take just an example to explain how this is working. So let's take the nickel 2, D8, spin 1, and so this is the energy diagram of our d orbitals with the electron in it. So what you can notice is we have now at this level here, we have two orbitals that are quite close in energy that have 3 electrons. So it means that here you have a first excited state that will correspond to the excitation of this electron here into this orbital. And when this takes place, you see that the 2 orbitals that are involved, so this is the orbital of the ground state, this will be the orbital of the excited state. So these orbitals have the same quantum number ml equals 2. So this means that in a first excited state, there is no change in ml, and this results in a contribution to the zero field splitting D parameter that will be negative. And this contribution might be large if the energy difference between these 2 levels is small. If you go further now, you take the second and the third excited states. So this is excitation of this electron into this or into this orbital. So this takes place with a change in the ml number. For you go from 1 to 2 or from 1 to 0. And this results in a contribution to D that will be positive. And the overall D you have for such a compound will be then the summation of all the contribution from the excited states. But because the largest is the first, the sign of D will be given by the sign of this first excited state. And in the case of nickel, we may expect a negative D parameter for nickel. And this indeed is what happens. So this is a result of some ab initio calculations where you can see that the value that we get by calculation for the contribution to D. So for the first excited state, we have a strongly negative contribution, and this is what happens due to this excited state. And yes?
Basic question. So may I so you think that negative D indicates the out of plane?
Out of plane?
Out of plane is the axis?
Yes, I will discuss that just later on. Yeah. Yeah. So just to show that indeed the calculation confirmed what just this simple scheme allows you to evaluate qualitatively. And the overall D calculated is minus 16.8, and experimentally we get minus 14, so a quite good agreement. So this is just to tell that it's not related just to one complex, it's really related to the geometry. So these are other compounds we have made, and this is the D parameter we have obtained from the magnetic studies. So in all cases, it's a negative D value. So you can now apply this to another metal. I briefly go to the case of cobalt. So cobalt D7. This is the energy diagram of the D orbitals, and what now takes place for cobalt is the first excited state is a jump of this electron into this orbital. You see the delta ml is different to 0. So this means we have positive contribution, and this is also the case for the next excited state. And for cobalt, you expect a positive D, an overall positive D. And again, this is confirmed by the calculation showing that all the first excited states are have a positive contribution, you end up with something that is quite large, but positive. And indeed, for this complex that we measured, the D is, sorry, here is a mistake in a sign, it's positive. So this is what we have as experimental D, again, in quite good agreement with what is proposed from the calculations. You can apply it the same again for iron, D6. I don't want to explain again. I think you understood how to do. The result for iron is, again, a negative D parameter calculated experimental. Also, for these compounds with a negative D parameter here, what is shown is the easy anisotropy axis. So, and you can see that the anisotropy axis actually is along the Z direction, or if you prefer, along the direction of the apical ligand. It is perpendicular to the pentagonal plane. So this applies for iron. The same is true for nickel. So again, for the iron, you see it's something we have for several compounds. So it's really something that you somehow you control. You know what you expect. And I just want to point to this. So this is a compound. Actually, it's this compound with which we made some chemistry. So we just substituted this chloride by a diamagnetic linker, and you see that the anisotropy is not changed. So this is really interesting because now we have building blocks that you can use to make chemistry and to implement well-controlled anisotropy into a more complex chemical system. So I mentioned at the start of my talk that to have a slow relaxation of the magnetization, you need a large spin ground state and Ising type anisotropy. Actually, this is what we have here in the case of iron. Spin 2, something like -10, between -10 and -20 for D. So the question was, can such a compound actually already behave as a single molecule magnet? Just a single iron center. The answer is yes, but when we take a compound and we measure let's say the slow relaxation of the magnetization, so we measure that with AC susceptibility. So there can be a component in the out of phase susceptibility. So this is what we call here chi-second, and this is versus frequency for different temperature. So this tells you there is a slow relaxation, but such a picture is also telling that in such a case, relaxation is quite fast. So not so interesting. So and this is mainly because in a solid state, the molecules are not so far from each other, and so there is dipolar interactions between the molecule, and this contributes to the relaxation. So what you can do is you just separate the molecule by doing some coordination chemistry. So here, this is the same compound I already introduced. So what we did is we used a nickel tetracyano compound as a ligand to substitute the chloride. And when you do so, you separate the iron centers. You don't change the anisotropy. And now, when you measure the slow relaxation by AC susceptibility, what you get is such a picture. And what this is telling is that you see the maxima here actually goes to lower frequency as you reduce the temperature. So this means that here we are in a thermally activated process. So you slow down the relaxation, and at a point, it's temperature independent. So from this kind of data, we can extract the relaxation time and plot it. And you can see here, this is a relaxation time versus inverse temperature. So in a higher temperature domain, we have a thermally activated relaxation regime, and then it's temperature independent. You can analyze that by an Arrhenius law, and you can extract the energy per year. That in this case is 49 K. So this is already a nice example. We have now iron and nickel that have quite substantial magnetic anisotropy. So at this point, the question was, can we do better? So can we get a larger anisotropy? So to get a larger anisotropy, actually what would be required is to have an orbital component that contributes to the magnetic anisotropy. So this means that ideally what we should have is a first order spin coupling. I told you this is something that in real compounds it's almost impossible, because in real compounds you never have the ideal geometry. But actually what you can do is you can try to design something that has a geometry as close as possible as to the ideal geometry. So ideal, you would have here 3 electrons distributed over 2 orbitals at the same energy level. So this is the origin of first order spin coupling. In the real system, ideally what you can expect or what you can target is something in which the lifting here is as small as possible. Yeah? And if this is the case, then you can reach something that is called a quasi-degeneracy. So this means you have not a full first order spin orbit coupling, but you have some contribution coming from that. And this is possible if you can design a compound that has small distortion and also with a very symmetrical ligand field surrounding the metal center. So for that we used this ligand. So with this ligand we have something with only nitrogen connected to the metal, and we have nitrogen that from a chemical point of view are very, very similar. So here we expect something where the ligand field is quite similar in the equatorial position. Moreover, this ligand is very rigid, and this means that there will be no distortion in the equatorial plane. And here are 2 crystal structure of these compounds. So we made them with iron, and in the apical position we have a halogen, a bromide, or iodide. So some ab initio calculation tell us that indeed the energy difference between these 2 orbitals that are the lowest in energy, the difference here is very small. So here we are in the order of 130 inverse centimeter. So very, very, very small if you compare, for instance, the energy level of the next orbital. You see that this is very small compared to the other ones. So this allows to conclude that we are here in a quasi-degenerate orbital system, and this is also shown by the calculation, because the ground and the first excited state are mixed. So there is really first order spin orbit coupling. And of course, when you are in such a situation, you cannot analyze anymore your data using the zero field splitting model. It's not adapted anymore. So this is why I don't provide the numbers for that, because we cannot analyze the data and extract a D parameter. But what is interesting is, so if I take this molecule and we measure the AC susceptibility, we see that we have a slow relaxation of the magnetization that already exists even when there is no magnetic field applied. In the previous systems, we had to apply a magnetic field to somehow slow down the under barrier relaxation phenomena. Here, it's not required. Here, even in zero field, we have already a slow relaxation of the magnetization. But there is also some faster components. So what you can do here is you make a solid solution of these compounds. This is, you take the iron compound and you mix it into a matrix of a diamagnetic system that is zinc, that has exactly the same crystal phase. And so you isolate your molecule, your paramagnetic molecule in a matrix. So you reduce the dipolar interaction between them. And then you get something that is shown here. Again, we have here a thermally activated process and then a faster process that does not depend anymore of the temperature. Here is the relaxation time versus temperature. And here you nicely see this thermally activated system. And now when we analyze that with the Arrhenius equation, we extract an energy barrier that is in the order of 90K. So this is for the iodide system, and this is for the bromide. And you see we have something that is very close. So this is with iodide, and this is with bromide. Some very related behavior. And this is telling that for these systems, we have a very large magnetic anisotropy. Okay, so these are some quite recent results. Later on in my seminar, I'm not going to use anymore these compounds because this is still work that is going on. Okay, so now we have interesting. We have the building blocks we were looking for. That is, we have metal complexes with iron and nickel that show substantial uniaxial magnetic anisotropy. So axial anisotropy means negative G values. They have a very good structural robustness. So this means that the geometry is not disturbed when you do chemistry in the apical position. And when this is the case, it means that the anisotropy is not changed when you do chemistry. So you know that in a compound you are going to get, the anisotropy is the one you had in the starting material. So these are then ideal units for the construction of some polymetallic species with magnetic anisotropy. So this is what we have done afterwards. So we have been using these complexes to design some molecular nanomagnets. So when you do that, at this step, you have some other aspects to control. That is a chemical topology of your system. So the chemical topology will, of course, also result in a spin topology. So if you want discrete or 1D structure, so this is something you have to control. You have also to have exchange interaction between your magnetic center, and possibly you can also introduce some additional features. So this is just to show that when we use these complexes, so here we have iron, here we have nickel. So the chemical system is quite same. We just change, and the third one also, we just change here for iron, for nickel, and here for cobalt. And when we measure the magnetic behavior for these compounds, we see that with iron, with nickel, we have a slow relaxation, so single molecule magnet behavior. But we don't have single molecule magnet behavior for the cobalt. And the reason for that is for the cobalt, we have a positive D, that is, there is no actual anisotropy. The anisotropy is planar, and this is not what is required to have a blocking of the magnetization in such systems. So the good building blocks are those with nickel and with iron, but this was expected. So when in a chain system, it's more or less like in a single molecule magnet, except you have a one-dimensional system, and in this system you have the spin that will be aligned, organized because of the exchange interaction, and you have then the magnetic anisotropy that can be used to magnetize your system in one direction or into the other direction. There is, again, an energy barrier to, let's say, to relax between this to this situation, and in this relaxation or this energy barrier depends on the anisotropy, but depends also on the exchange interaction that applies in this system. So when you design that, you have to take into account all these aspects. So here's a first example of such a chain. So this is the building unit we used. So an iron complex with a macrocyclic ligand. So this compound was associated with a famous niobium complex. So this is spin 2, this is spin half. When you do the chemistry, you get this one-dimensional system in which you have an alternation between niobium iron along the chain, and on the side of the chain you have some additional iron complexes, and this is just a simplified view of this chemical system. We have the expected slow relaxation of the magnetization. So here I show chi prime and chi second. So you already recognize the feature of the slow relaxation that is given by the chi second component. You can analyze this data and you find an energy barrier for the spin flipping that is in the order of 74K. I told you this low-dimensional compound behave like a real magnet. So this means you have also hysteresis that appears. And for instance, for this compound here, so this is a magnetization versus applied field. So from 0 to positive values, the field is applied in one direction, and the negative values means the field is applied in the opposite direction. And here you have the magnetization, and you can see that when the compound get magnetized and you reverse the magnetic field, you see the opening of a hysteresis loop. So in red is what we have seen at 1K, and if you go to even lower temperature, this is not changed. But please note, we have to go to very low temperature to see that in this compound. So this was already a very nice result, but it was a little bit disappointing because I expected here something that would be much larger. And the reason why the energy barrier is not so large is actually shown in this picture. So I told you that we know what is the direction of the anisotropy axis of these complexes. So if the red arrow here just show the direction of the anisotropy for each of the iron center. And what you can see here is that they are quite tilted. So this means that the macroscopic anisotropy for this compound is not so large. Yeah, because of the tilt of this direction. So to get a better anisotropy, the ideal situation is to have all the local anisotropy aligned into one direction. So this is something that is very important, and it's also something that chemists can manage to do. For that, what we did is we used another linker that here is a chromium complex with 2 cyanides in a para position. So this means now we have a linker that will link at 180 degrees to iron center, to metal center. And when we use it and you react it, for instance, with this nickel complex, we indeed get a chain in which we have alternation between chromium and nickel, and this chain looks quite straight. And indeed, if you look now from the crystal structure, if you compare the pentagonal plane here, this is in purple, and for the second nickel here in yellow. So the angle between these two planes is very close to 0. So this means that they are more or less stacked in parallel. And the result of that is the magnetic properties. So first, here what I show is the chi-T product versus temperature. So chi-T, if you're not familiar with that, this is just a different unit equivalent to mu effective. And what you see is when you reduce the temperature, you increase the magnetic moment of your species, and this is characteristic for a chain system. Magnetization shows also that for a very weak field, you have a very fast magnetization. So this is also what you expect for such a spin chain. You can analyze, extract exchange interaction, and this exchange interaction is in good agreement with the exchange interaction we get just for a discrete 3 nuclear species with the same ingredients. So ferromagnetic and an exchange interaction that is ferromagnetic in the order of 10 inverse centimeter. We have also the correlation energy you can extract from the plot of the log of inverse temperature, and we get here a stabilization energy due to exchange interaction that is in the order of 20K. So all is right here for magnetic behavior corresponding to a chain system. And now the slow relaxation. Again, you see the typical picture of chi-second versus frequency, and you see that when you reduce the temperature, the frequency of the maximum here goes to lower frequency. So here we are really in a thermally activated relaxation regime. This is a plot of the relaxation time versus inverse temperature, and we can extract the energy barrier for this system that is again shown here. So in this case, we have a ferromagnetic single chain magnet. So this is typical of what you expect. We can do better. We change now the nickel for the iron. Why should it be better? Because you go from a spin 1 to a spin 2 system, the same nickel complex, and you get again a chain compound in which the anisotropy axis, so this is obtained from calculation. The blue arrow is the easy axis anisotropy, and what you can see is for the metal centers, the easy axis is more or less pointing into the same direction with a tilt that is below 10 degrees. The magnetic behavior, again, typical of the spin chain, with some ferromagnetic interaction between chromium and the iron. Again, a correlation energy that is in the order of 20K. And if we move now to the slow relaxation behavior, what we can extract from the AC susceptibility data is here's a plot of the relaxation time versus inverse temperature. And what we see here is two relaxation regimes. This is often seen in this kind of compounds, because what you have is the contribution of the infinite size regime. So this means that your chemical system is large enough to behave like an infinite system, but you may also have broken chains in your system, and then we see what is called the finite size effect. But this is quite usual. You can analyze that, and when you analyze these data, what you see is that now we have pushed the energy barrier for spin relaxation above 110K. So this is
why you are different size. 5.6 Kelvin.
Because
coming from the defect?
Yes.
Defect.
Actually, this is a crossing. This is a crossing between the two.
It's coming from defect.
This is coming from defects that are broken chain, because for the iron system, it's very difficult to crystallize. So we get very tiny crystals. So this means the chain is not so long.
Do you control the concentration of defect?
No.
All time is the same.
No.
If you make roughly.
No, it's never the same. It's never the same. Actually, it depends on how the sample is crystallized. If you get larger crystals, you may see no defects. But when you crystallize and you make very small crystals, then you see defects, because actually what we call defect is just short chain. Because when the crystal has a size of, for instance, 100 nanometers, it means that the chains are not so long. Okay, so for the iron, we have very small crystals. With nickel, we get larger crystals, so we don't see the defects. Yeah. And for this system, we have, of course, also opening of the magnetic hysteresis. So this is the magnetization with the field up and the field down. So very nice hysteresis. And what you can notice is we see the opening of the hysteresis already below 5K. In the first example, we had to go to 1K, and here we see it already below 5K. So this means that indeed the blocking is much more efficient for this compound. Okay, so this is just to point that when you design such kind of single chain magnet, it's very important to design a system in which you control also the direction of the magnetic anisotropy. So you have to implement large magnetic anisotropy, but you have also to control how this anisotropy will be organized in the macroscopic system. A small development we currently do with this kind of compounds is to implement some other property to this system. And here what we try to do is to make a chiral single chain magnet using the same building block. And what we do is actually we have developed some complexes with a chiral ligand. So now the pentadentate ligand here is chiral. So we have chiral centers that have been introduced to the ligand. So this means that now we have here one enantiomer of metal complex. So if you take the ligand with the opposite chirality, you get the other enantiomer, and these are just the mirror image of the other complex. So now we have a starting material that is chiral, and of course, if you make a polynuclear system with it, you are going to develop some chiral structures. So here, for instance, we used again the nickel cyanide to make a coordination complex, and we get helical chains. When you start with the air enantiomer, so if you do the chemistry with this one, you get this helical structure that turns left. But if you do the chemistry with the other enantiomer, you get the same chain, but here now it turns right. So this is just controlled by the chirality of the starting material. This is also confirmed by the CD spectra of these two compounds. You see that the signal of one is just opposite to the signal of the second. So it means really we are dealing with enantiomeric systems. Magnetic anisotropy is not changed. So here we can again assess the anisotropy, and in this case here we have a D that is in the order of -10. We made also a system that is a real single chain magnet, that is with exchange interaction between the magnetic center, and this has been obtained when reacting this chiral complex with iron Cl2. Actually, what happens when you do that is the chloride from this complex connects to the iron, and we have iron Cl4 minus, that is a tetrahedral species that is connected to the 7-coordinated metal center, and this develops this chiral chain structure. Again, we can do the two enantiomers, just changing the starting material. This is the information we get from calculation about the magnetic anisotropy that is located on each of these two centers. So for the tetrahedral iron, we have a positive D, whereas for the 7-coordinated iron, we have the expected negative D. And as you can see here, now we have very large values of D, and this is because of the ligand field in the apical position that is weaker. And for this compound, we have indeed a slow relaxation of the magnetization as shown by the out-of-phase susceptibility versus temperature. But you may also notice that for this compound, we have a magnetic ordering that takes place for higher temperatures. So first we have antiferromagnetic ordering around 5K, and it's only below the ordering we see this slow relaxation of the magnetization. So maybe you may ask yourself why we are interested in making such kind of chiral nanomagnet. Actually, the reason behind is what we target is some magneto-optical properties. Yeah? And to finish, I would just show you briefly a result we have showing some magneto-optical effect, but for a different system. So the system here we have been studying is a lanthanide complex. So this is just a drawing of the complex. So here, this is a complex in which we have a lanthanide center and everything else is diamagnetic. And we wanted to have a chiral center here. And for that, we have used some ligands that are anions that are optically active. And so we have the two enantiomer of the anion. So when you connect this anion to the metal center, you get one complex with one given chirality. Here it is lambda for the dysprosium. And if you use the other enantiomer of the ligand, you get the same complex, but the other enantiomer. And in this one, the chirality of the lanthanide is delta. So again, this is proven by the CD spectra. And these complexes are single molecule magnets. They show a slow relaxation of the magnetization at low temperature. And this is for the dysprosium sample. But for these compounds, there is also some luminescence. So we measured the luminescence on the solid state and on single crystals. So this is a setup that was used. So these are the crystal of one complex. So we have here one enantiomer of the complex, and this was put on this device. So one enantiomer, the other enantiomer, so these are crystals, and we measured also powders, and the powders are just crushed crystals. So here are the details if you are interested in that. Just briefly the results. So what we see is indeed the expected luminescence for the dysprosium. So this is what we have for our sample. So this is just something from the literature, just to point that what we see corresponds to what is expected for the dysprosium. But then there is something happening. So if you go from if you lower the temperature, so what you can see is that the luminescence shows a difference between the left-handed and the right-handed circular polarized, so the right-handed and left-handed luminescence. So in green you have the right-handed light, and in purple the left-handed. So as you reduce the temperature, the right and the left-handed signal becomes different. So this has been measured here for the lambda enantiomer. You can do the same with the delta, and you see the same phenomena when you reduce the temperature. So this means here we have circularly polarized luminescence that take place for these compounds. And this is the GLM you can extract from this data. So here I plotted for the lambda and for the delta. So here we have really a polarized luminescence. The GLUM is quite large for this kind of compounds. And another thing is that the degree of polarization decreases when you go from low temperature to higher temperature. And interestingly, the CPL and the increase of the GLUM actually the temperature range is the same temperature domain in which we see the slow relaxation of the magnetization.
Excuse me, so may I make sure that you measure the circular polarization of emitted light?
Yes.
Not incident.
No, emitted light. It's a luminescence.
So you analyze them?
Yes, just the emission. Yeah. Yeah. So At this point, the question was to know if is it the magnetic moment of your metal ion that has an effect on the luminescence, or is it just coming from a structural factor? Because CPL can just, usually people have a CPL just because of a chiral structure. So to check that, what we did is we did the same complex using europium that is also luminescent, and then we measured the luminescence going down the temperature down to 5K, and at 5K, there is no dichroism. So the right and left-handed is exactly same. So this suggests that it's not the structure that is at the origin of this CPL for the dysprosium, but actually it is really an effect of the magnetic moment of the metal center here, and this is why we see the CPL together with the appearance of the slow relaxation of the magnetization, and this suggests that there is a synergy between the blocking of the magnetization and the CPL that we see for this complex. So this is a behavior that is very similar to what is called the magnetic circularly polarized luminescence, but here this is induced by the intrinsic magnetization of this complex. Okay, so this was just to illustrate why we are interested in these magnetic and chiral species. So just to finish, I would like to sum up what I was telling today about the pentagonal pyramid complexes. So if you are looking for compounds with controlled magnetic anisotropy, maybe this is the kind of complexes you should look at, because you can manage anisotropy that is having D from -30 to roughly +30, depending on the metal center. For us, most interesting was iron and nickel, because it is Ising type anisotropy, and these complexes are robust, so you can do chemistry with it. And it's also because of the ligand, it's also a versatile chemical platform to implement some additional property. I have shown that we implement some chirality by making chiral ligands. Regarding the SMM and SCM behavior, a very important point I would like to stress is it's very important to design a compound in which the local anisotropy are aligned in the same direction, because this will have a significant contribution to the energy barrier of the relaxation. And this is another point I did not discuss today. This is because of the bending you may have in your polynuclear system. With that, and before finishing, I just would like to acknowledge the people that have been involved in this work. So these are all in yellow. These are all students that have been working in this project, PhD students, but also postdoc. These are some people, permanent staff of my group that are involved in this project, and some very important collaboration. One very important collaboration is with Professor Guéry and Suo. These people are doing the ab initio calculation, and this is something that is very useful and was very important to understand and to rationalize a little bit the magnetic properties and the magnetic anisotropy of these complexes. And then a very efficient collaboration with Professor Ramashesha, who was making the modeling of a large polynuclear system, and Anne-Laure Barra, she was doing high-field IPA just to confirm by this technique the anisotropy we extracted from the magnetic studies. And with that, I would like to thank you for your kind attention.